Welcome to this video. We're going to learn about mechanical energy and the fact that it's conserved. Now, mechanical energy is an umbrella term. There are lots of energies that we can study in physics, including nuclear energy, chemical energy, and lots of other stuff. Some of these energies pertain to the current unit. They include kinetic energy and potential energy. Potential energy has two types. There's the energy when a ball or object is elevated a height. That's called gravitational potential energy. And then there's the potential energy that a spring has, or another elastic springy object has, when it's compressed or stretched. And that's called elastic potential energy. Because elastic means it can return to its original shape. It stores up energy when it's compressed or deformed. And both of these are under the category mechanical energy. Mechanical energy is defined as the kinetic energy plus all of the potential energies added together. So another way we could write the definition, we could say it's the kinetic energy plus the gravitational potential energy plus the elastic potential energy of a system. And this is the definition of mechanical energy. Now, mechanical energy is a really useful thing for us to talk about. And the reason is because the total amount of mechanical energy is conserved, which means stays the same. The amount of it stays the same. When the system we're looking at is isolated. Isolated means there's no friction, there's no applied force by a person acting on the system, there's no other forces doing work on the system, except for the forces that are inside the system. So it's conserved, it stays the same. Here's what that means. If you have 10 joules of mechanical energy right now, then in an hour, the system will still have 10 joules. The amount doesn't change as time passes. So we can write that like so. The amount of initial mechanical energy, like right now, is equal to how much you have in an hour, the final amount. This equation can be expanded. On the left side, we could replace the initial mechanical energy with the initial kinetic energy plus the initial gravitational potential energy plus the initial elastic potential energy. And on the right side, we could do the same thing. The final kinetic energy plus the final gravitational potential energy plus the final elastic energy. But we could even go farther than that. We know the formula for kinetic energy. So we could replace this with 1/2 mv final squared, v initial squared on the left, and 1/2 mv final squared on the right. V initial squared, right here will be 1/2 mv final squared. We know the formula for gravitational potential energy. It's mgh. So we put h initial, since the height can change. Here we put mgh final. And we know the equation for elastic potential energy, right here and right here. It's 1/2 k, the spring constant, the stiffness, times x, the compression, squared. And the compression can change, so we do 1/2 kx initial squared and 1/2 kx final squared. Because x initial, x final, those could be different. You can compress and then let the spring go. Now, while it's true that the total amount of mechanical energy is equal at two different moments in time, the amount of kinetic energy can change. the amount of gravitational potential energy can change, and the amount of elastic potential energy can change. These things can be converted into each other, sort of like a bar graph, right? You have kinetic energy, you have PE gravitational, PE elastic, and then there's a final moment where we could graph how many of these things we have, how much of the things we have, like KE and PEG, PE elastic. And let's say we have, at the beginning we have a lot of kinetic energy and nothing else. As time passes, we can take that kinetic energy and it's possible to transform it into other types. So if the object slows down, loses kinetic energy, it might gain some height, and also there might be a spring that gets compressed. So the amount of potential energy can change, the amount of kinetic energy can change. You can convert this into these. But the total, when you add up both of these columns together, the total has to equal the total on this side. We're going to use this to solve problems. Let's take a look.